Now, if we consider an infinitely long wire carrying current I in free space, by symmetry we'll know that the magnetic field will be circles. Well, if we go back to the early 1800s, it was observed that current carrying conductors will behave like magnets. If you have two conductors with current in them, they will either attract or repel. So that was observed in the early 1800s, and then afterwards it was quantified, and now we know how to calculate the magnetic fields. Anyway, by using the right-hand rule, we can determine the relationship direction-wise between current and magnetic field. And what is the right-hand rule? You should remember from physics that if the current is the direction of the thumb, then the magnetic field lines will be like the fingers. In this case, if the current is going as shown, like the thumb, then like the fingers, so that will be the direction of the magnetic field. And from symmetry, there will be concentric circles, 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 getting weaker and weaker as you go away from the conductor. Later on in the 1800s, the relationship between electric current and magnetic fields was quantified in Ampere's circuit law, which basically states if you integrate H along a closed contour H dot dl, that will equal to the sum of all the currents enclosed within that particular contour. Before we move on to calculations, the right-hand rule gives the relationship between current and magnetic field, or if the current is in circles, then the magnetic field will be as the direction of the thumb. For example, if we look at this here, if the current is going like this, it will be like this, and that's enough. So you can see, if you apply the right-hand rule, will give you the flux lines. We'll use the dot and the cross notations. Now the dot here indicates current or an arrow coming out of the paper, and if you remember the cross notation, this will indicate a vector going into the paper. This represents the end of the arrow, the cross. So we use the dot notation. This is now the current I. The circles will be like that. We take a point at a distance A away from the current carrying conductor, and a small angle delta theta. This length of the arc, will be the radius, the length of this arc, we call it delta L, equals the angle, which is delta theta, multiplied by the radius, which in this case is A. So to apply Ampere's circuit law, we will integrate from theta equals to 0 to go all the way around. That will be 2 pi HR d theta. Actually, R here is A, and that will give you H at point A equals 1 over 2 pi A ampere per meter. The relationship between H and the flux density B is mu naught, where mu naught is the permeability of the free space. So now we have considered the magnetic field due to an infinitely long current carrying conductor, and we were able to calculate it. This is the case we considered earlier. We could have got exactly the same results if instead of current I here, we had n conductors, each carrying I over n, because what matters is the total current enclosed by the contour, and that's what's written here. Generally, we will use the current enclosed, the sum of all the currents enclosed by a contour. We call them magnetomotive force acting on the contour. We will call it F. And generally, in this particular case, we had our magnetomotive force, the force that is creating the magnetic field, is I. It could have been N conductors, each carrying I over N. Could have been anything else. Generally, we'll call it F, where F is the MMF, or magnetomotive force. Now, we bring a tube, an iron tube, and place it around the current carrying conductor. The flux density here, BA, will be much higher. Why is that? H will be the same, but B is mu R, mu naught. Mu naught is the permeability of the free space or air. Mu R is the relative permeability of iron, and if the iron is not saturated, mu R will be very large, several thousands, and we conclude from that in iron, very low values of H give us large values of B. And if we actually change the position of the current here and we move it a bit to the left or a bit to the right, the flux density in the iron is not going to change much. So the flux density in the iron is largely independent of the position of the current. Well, infinitely long current carrying conductor and infinitely long tubes are not a realistic proposition. So now we will look at some practical magnetic circuits. We will take something very simple and then we will start modifying the simple shape we're starting with until we get to the end towards a typical shape of laminations that are used in electric machines. The main reason for this logic of the presentation is to show you that we're starting from very basic principles. Engineers start from very basic principles and end up building and creating and designing products. So we will consider this magnetic circuit. The cross-section area of the iron is as shown. I've chose mu R for the iron at certain value. Actually, I'm just playing with the numbers to end up with very simple numbers to manipulate. This is not a typical value. And if we have a coil of 50 turns and carrying a current of 1 amp, if you apply the right-hand rule, the current in the coil is going this way, so the flux lines will go like that. And I will assume that the length of the average length of the path, the flux path in the core is 0.5 meter. Again, I'm choosing numbers to give me to ease the calculation. You will see that in a second. We look at this red flux contour. The magnetomotive force that is acting on this flux contour is the total current enclosed by the contour, and the total current enclosed by the contour is 50 turns multiplied by 1 amp, so it's Ni. Apply Ampere circuit law. F is Ni, and H.dl, we know L is 0.5, and they will give you H is 100 amp per meter. From that, B is mu naught mu R H, and here is my mu R. This is the mu R, and will give you a nice figure, 1 Tesla. Tesla is the units of flux density, or vapor per meter square. Vapor is the unit of flux, meter square is the unit of the area. From that, the flux is the flux phi is flux density multiplied by the area perpendicular to that flux. B is 1, A is 10 meters, well, 10 actually centimeters square. So let me just remove this. So in meter, the 10 centimeters square be 10 to 10 multiplied by 10 to the minus 4. It will give me 1 milli vapor, or 1 10 to the power minus 3 vapor. So that's the flux phi. Why did I go for the concept of magnetomotive force? Because now we have something similar, treatment similar to electric circuits, and I believe you all should be more comfortable with electric circuits. So we have phi is B multiplied by A, that's B is mu H, H is F over L, and you end up with phi is F, magnetomotive force multiplied by this. Rearrange it, we end up with the flux phi is the magnetomotive force F divided by the reluctance, where the reluctance, I showed the reluctance as L over mu A. So in electric circuits, you have the voltage, or EMF, electromotive force, applied on a resistance R. The current I goes in a closed loop, and Ampere circuit, well, not Ampere's, Ohm's law is V, I is V over R. Magnetic circuits, with using this equation, we can say we have magnetomotive force, in this case is Ni. It derives a flux phi across a reluctance R, and the equivalent relationship here to Ohm's law is phi is the magnetomotive force over the reluctance. This will enable us to treat magnetic circuits in the same way we treat electric circuits. But where did I get this from? I actually got this from Ampere's circuit law. So this Ampere circuit law formation and the magnetic circuit concept are the same thing. It's a mathematical manipulation. Now we consider a core as shown, but I cut a small air gap. The air gap is 5 millimeters compared with the flux path in the iron, which is 300 millimeters, just to show that this is very small. But let's see what effect this small air gap has on the value of the flux. We calculate the reluctances. The reluctance of the core is the length of the core divided by mu naught mu r, area of the core. Give this value. The reluctance of the gap is the length of the gap, and here mu r is 1, so it's mu naught. Give us this value. Straight away you can notice that the reluctance, magnetic resistance to the flow of flux due to the 5 millimeter air gap is much greater than the reluctance, the resistance to the flow of flux in the iron path. Well, let's look at the magnetic circuit equivalent. F, phi, RC, we have this reluctance in series. Consider these two reluctance in series, calculate the flux, get 10 to the minus 4 vapor. If we ignore RC, the core resistance, the 300 millimeter, we end up with the same value. What we conclude here is, if the iron is not saturated, because the iron core has very high permeability, the reluctance of the iron will be very small. And in most of our calculations in electric machines, we can ignore, in the first instance, ignore the reluctance of the iron. This is like electric circuits when you have cables connecting an electric source to a load. When you're calculating the current, you don't take into account the resistance of the cable. Why? Because you know the cable have resistance, electric resistance, but it's very low compared with the resistance of the load. This is similar situation. We use the iron core here to carry the flux, but this flux is supplied to the air gap, which is the highest reluctance by far in the circuit. In other words, we can assume that the magnetomotive force Ni is acting on the air gap approximately. In this case, the integration of H dot dl will be H multiplied by G. This part here is the integration of H dot dl approximately will equal to H multiplied by G. Ignore the rest of the part of the integration. H will be Ni over G, and B will be mu naught, because it's air gap, Ni over G. And this will give us readily a very close but reasonably accurate value of the flux density in the air gap due to magnetomotive force given by Ni. We know now what reluctance is. Now we consider inductances. Inductances are associated with magnetic fields, and you would recall seeing them in equivalent circuits of electromechanical devices. Also, any of you who did power electronics would come across situation when we say we use an inductor, or even in filters and low signal electronics use inductors. Terms such as self, mutual, and leakage inductances are used, but what do they mean? We consider here a three-turn coil. What I'm going to introduce you now is to the term flux linkage. So we consider this three-turn coil. I'm just expanded it, and we look at the current. If the current is I going as shown in red, then apply the right-hand rule. You will find that the flux, let me just apply the right-hand rule again, going this way. Well, yeah, the flux lines will be as shown. You can see that the first turn here is linked by 1, 2, 3, 4 flux lines. And the turn at the end similarly is linked by 4 flux lines. The turn in the middle is linked by 1, 2, 3, 4, 5, 6 turns. So flux linkage is total flux linkage. You look at the flux that is linking every turn of the coil. The first turn is linked by 4, the middle turn by 6, the last turn by 4. So total is 14, and that's actually 14 vapor turn. That's the units of flux linkage. Definition of the self-inductance, L, is flux linkage over current. And for self-inductance, the flux linkage is caused by a current in the coil itself. Now, if all the turns of the coil were linked by the same number of flux line phi, so if all the turns were linked by phi, then lambda will be n phi. That's approximate. And you will find in many books and equations, they just consider n phi as the flux linkage. That is not the general case. Now we know what the self-inductance is. Let's look at mutual inductance. What we have a coil here, coil A, excited with current. That current produces flux lines, and these flux lines are going like that, and of course they all go in closed contours. Then we bring this coil on the left. We bring this coil here to the proximity of coil A. This coil now is linked by flux generated by coil A. So these flux lines in the middle here, they link both coils. So these are mutual flux. If our aim was to introduce good magnetic coupling between the two coils, then our aim would have been to increase the mutual flux, make the coupling of the coils very, very large. If you look at flux lines like these are not linking, these are not mutual, these are not linking the coil, the second coil, and we call them leakage. You have to remember, leakage, you define leakage, you have to define a flux path. For example, if you have a pipe carrying water from A to B, any water that is leaked in the way that doesn't reach B is leakage water. If your aim here is to create flux in coil A that links coil B, any flux that doesn't link coil B, then it's leakage. So leakage flux has to be defined on a circuit. Anyway, this is an introduction to what is self-inductance and what is mutual flux and inductance, and what is leakage flux, and of course every flux component is associated with the corresponding inductance. We look at the self-inductance of a coil now. This is a coil. For a compact coil like this, the likelihood of all the turns being linked by all the flux lines is higher than if you have a long coil. Anyway, this coil is represented by this magnetic circuit and the flux line as shown. Then you can define L. We know L is lambda over I. You can use the equivalent magnetic circuit. This is the magnetomotive force and the flux goes around. Again, back to this, if we assume all the flux lines link all the coil, lambda will be N phi. But from here, phi is F over R, F is Ni over R. That will give you N squared. I will cancel I. It will give you inductance N squared over R. Remember, R was the length of the magnetic path over mu naught, mu R, whatever, A. So this depends on the dimension. This depends on the parameters of the coil. So actually, all inductances are function of the geometry of the magnetic circuits. So this shows that the self-inductance is N squared, the number of the coils turns, divided by the reluctance. And here we are assuming that all the flux lines phi link all the coil turns.